In this video tutorial, we will be discussing the concept of refraction. Refraction is the bending or changing in direction of light when it travels from one medium, or one substance, into another. So as light moves from water into air, for instance. I'm sure we've all seen this example before. Maybe not with a pencil, because what kind of monster does this, but probably with a straw or a stirring rod. We know the pencil is not bent like this, and if you took it out of the water, it'd be one straight solid piece. So why does it look like it's snapped in half? As I had mentioned previously, we don't see with our eyes, we see with our brain. And your brain always thinks that light travels in straight lines only. So as the light from the coin leaves the water and enters into the air, it refracts, changing its direction until we see it with our eyes. Our brain, thinking that light only moves in a straight line, backtracks it and predicts the coin's location to be somewhere here, when really it's down here. So what causes refraction? Well, light travels at different speeds in different mediums. Think of this wagon as it moves from pavement into sand. As soon as this wheel touches the sand, it starts to slow down. But these three other wheels are still on the pavement, a much smoother surface, so they're able to maintain the same speed while this one wheel slows down. And when this wheel moves faster than this wheel, the wagon begins to change direction. Well, that's what's happening over here. When light rays move from one medium, one substance, into another medium, a different substance, one side enters the second medium while the other two are still in the first medium. Just like the wagon going from pavement to sand, we start to see a slowdown on one side while the other ones are still moving quickly. This difference in speed causes it to change direction. The opposite occurs when the light exits that medium. The side that entered in first is also the first to leave. So now it is speeding up while the other two are still stuck in the second medium. This causes it to change direction again, except this time it's bending in the opposite direction. So if the wagon were to exit onto pavement again, this wheel would be allowed to move faster while these other three are still stuck in the sand, moving slowly. This causes the wagon to change in this direction, bending its path again. As we mentioned earlier, light travels at different speeds in different mediums. In a vacuum, meaning there's nothing there, nothing to slow down light travels at a constant 3 × 10⁸ meters per second. This is the fastest speed in the known universe based on our current understanding of how the universe works. Nothing can travel faster than this. This is the top speed for light. But when light enters water or acrylic, which is a type of plastic, it will slow down significantly. We say that these substances have different optical densities. Now just be aware that optical density, grade 9 density, is based on mass and volume relationships, while this one is based on how light behaves in these different substances. Now when it comes to refraction, many of the concepts we used in reflection are very similar. So we still have a normal, the imaginary line that is perpendicular to the phase boundary. So perpendicular meaning 90-degree angle. And instead of a mirror, we have a phase boundary. That's where two different mediums meet. So water and air, for instance. And this would be the border between them. The light coming from the object is still called the incident ray. But instead of reflecting backwards like you would if this was a mirror, it refracts. So we call this a refracted ray. We still measure the angle of incidence from the incident ray to the normal. So don't do it from the phase boundary to the incident ray. It's always measured from the incident ray to the normal. So that hasn't changed. But now we talk about the angle of refraction. So it's not reflecting back, but it's refracting out. Again, we always measure the angle from the normal to the ray. In this case, the refracted ray. So we call this the angle of refraction. Now the symbol for the angle of refraction is theta with a capital R. When it was reflection, we used a lowercase r. So be careful. Lowercase r, angle of reflection. Capital R, angle of refraction. Now the angle of incidence doesn't change. It's still theta I. There are two rules we need to be aware of when dealing with refraction. The first is that the incident ray, refracted ray, and the normal all lie on the same plane. That's very similar to what we learned when it came to reflection. In that case, the incident ray, the normal, and the reflected ray all exist on the same plane. So you didn't have the light coming in, then bounce towards you. You didn't have the light coming in, then bounce away from you. It was all on the same plane, as if you had a flat piece of paper. Well, the same goes for refraction. When the incident ray comes in through one medium and it goes into the water, for instance, it must stay in the same plane. It's not going to go refracting in and then refracting out in a weird angle. All right, it's always on the same flat plane. Furthermore, the incident ray and the refracted ray are on opposite sides of the line that separates the two media. So that line that separates the two media we call the phase boundary. Now the second rule of refraction states that light bends towards the normal when the speed of light in the second medium is less than the speed of light in the first medium. However, light will bend away from the normal when the speed of the second medium is greater. Now this rule is kind of confusing to me, so I usually just draw a picture. So here we have a situation where I have the phase boundary between air and water. I'm going to pretend my light rays are going to be this little wagon again with 4 wheels, and this dotted line is the normal, and that is supposed to be 90 degrees or perpendicular to this phase boundary. Now water is more optically dense than air, so light travels faster in air than it would in water. Just like you. Hopefully you move faster in air than you would in water. So when this wagon breaks through, this wheel on the left over here is going to encounter a much faster, less dense medium, and so this wheel will move faster. Certainly faster than these other 3 wheels that are still in water, a more optically dense medium where light will travel slower. So with one faster moving wheel and one slower moving wheel, it begins to turn to the right. Instead of traveling along a straight line, it bends away from the normal, refracting along a different path, and not this one. So that's what they mean here when they say light bends away from the normal when the speed of the second medium is greater. So the speed of the second medium, so this is the first medium because it was started off here, second medium is where it ends up. The second medium is faster, so it's going to bend away from the normal and start refracting in this direction instead. And of course the opposite is true if we switch these two mediums. Now that I'm going from air into water, this wheel slows down while these other 3 wheels are moving fast. This causes the wagon to change directions towards the normal, and instead of traveling straight ahead, it now bends and refracts towards the normal. So it's closer to the normal now than it was before. So again, light bends towards the normal when the speed of light in the second medium is less than the speed of light in the first medium. So the speed of light in the second medium is less than the speed of light in the first medium. It now bends towards the normal. Now I'm sure many of you have seen this phenomenon before, where if you look at water from just the right angle, it almost looks like the surface of the water is acting like a mirror. Instead of refracting light out, it's reflecting light back in. But how does a transparent substance like water reflect light back when it's supposed to let light through? Well, this phenomenon is called total internal reflection. Now this phenomenon only occurs if you're moving from a slow medium to a fast medium, because we need the refracted ray to slowly move away from the normal. And as you tilt the angle of the object's light rays into a more extreme angle, the refracted ray gets further and further and further away from the normal. And eventually it'll get to a point where refraction becomes reflection, bending so far away from the normal that now it goes back into the original medium. As such, the angle of refraction, which we always measure from the normal to the refracted ray, can never be greater than 90 degrees, because once it's past 90 degrees, now it's back inside the original medium. And we call this total internal reflection. So this is called the diver's window, because when you go scuba diving or when you dive underwater, if you look directly above you, you can see the sky. That's because if you look fairly straight up, so if your theta I, your angle of incidence, is very small, your refracted rays are able to escape out of the water. And of course, if it can escape out of the water, it can also go into the water. And that allows me to see out into the sky. But once my theta I, my angle of incidence, is too large, refraction turns to reflection and I can no longer see the sky. I can only see the bottom of the ocean. Which is what this is. Down here is just a reflection of the ocean floor, while up here is the sky. If you look up with a low theta I, you can see the sky, but looking with a larger theta I, you only see a reflection of the ocean floor. And that is called the diver's window. Alright, so now that we know what refraction is, let's take a look at the mathematics behind it, because I know that's exactly what you want to do. Now, n is the index of refraction. Different substances have different indices of refraction, and this is a ratio or a comparison of the speed of light in a vacuum, so the maximum speed that light can travel, versus how fast it's traveling in different substances. So as the index of refraction gets bigger and bigger and bigger, the speed of light in these substances gets slower and slower and slower. Meanwhile, the closer the number is to 1, the closer the speed of light is to its maximum top speed of 3.00 times 10 to the power 8 meters per second. All right, so small index of refraction, light moves fast through it. Large index of refraction, light moves slowly through it. And each substance has its own index of refraction. All right, so let's try a sample question, and again, we'll use the grass method for this. So given the speed of light in a sample of glass is 1.9 times 10 to the power of 8 meters per second. So c is the maximum speed of light, 3.0 times 10 to the power of 8 meters per second, while v is the current speed of light in whatever medium it's traveling through right now. So I'll write down v is equal to 1.9 times 10 to the power of 8 meters per second. It then goes on to say that the speed of light in a vacuum is 3.00 times 10 to the power of 8 meters per second. So I'm going to write down c is equal to 3.00 10 to the power of 8 meters per second. It then asks for the index of refraction for this glass. The symbol for index of refraction is n, so I'm going to say n of the glass. Since the equation is n is equal to c over v, I can then substitute my values in. C is 3.0 10 to the power of 8, v is 1.9 10 to the power of 8, divide these two values, and I get n glass is 1.58. I then write out my final statement. The index of refraction for this glass is 1.58. So I'm going to let you try these questions out yourself. At the very end, you can compare your answers at the very bottom of the page. But let's try question 2 together. So let's use the grass method again. Given, what is the speed of light? So that's what I'm trying to calculate. R, the speed of light in water. Given that water has a refractive index of 1.33, so n of the water is 1.33. Obviously, I'm going to have to use this equation. N is equal to c over v. But there's a slight problem. I have n. I'm trying to find v, but I have no information about c. But yes, you do. c, the speed of light in a vacuum, is constant. It will never change. It's always going to be 3.00 times 10 to the power of 8 meters per second. Now, that's not entirely true. It's more like 2.99 something, but for your convenience, we simplified it down to 3.00 times 10 to the power of 8. All right, so c value does not change. It's always going to be this. So I'm going to substitute the values in, then rearrange my equation, and I get 2.26 times 10 to the power of 8 meters per second. You can then write down your final statement, and we're done. So again, try out these questions yourself and compare your answers to the ones at the very bottom. Now for the next set of calculations, we're going to use something called Snell's law. Since many of you haven't taken grade 10 math yet, you probably aren't as familiar with trigonometry. Now this symbol, theta, you should know. Theta I is the angle of incidence, while theta R is the angle of refraction. Now Ni is the index of refraction for the incident ray. So whichever medium the incident ray is currently in, that is the n value you should be using. While Nr is the index of refraction for the medium where the refracted ray is entering, whatever that may be. Now this symbol over here is called sine, and it is a trigonometric function. Now I'm not going to go too deeply into this because that's a whole math lesson unto itself, but the sine function is often used when we're working with angles. Now you can't just press the sine button by itself. That's like pressing the division button on a calculator and not putting any numbers in. It doesn't do anything by itself. Well, similarly, pressing the sine button on the calculator does nothing unless you put in an angle to work with. Now, this is the most common calculator I see with my students, and you can find the sine button right here. So it looks like this if you want to look close up. So let's try a quick little sample calculation to make sure you know how to use the sine button properly on your calculator. Let's say I wanted to know what the value was for sine 45 degrees. Well, the answer should be 0.707 ... There's a bunch of other numbers in the end. Now, most calculators will let you press the sine button first, then you type in the 4, the 5, then an equal sign, and this should pop up. However, some calculators do it the opposite way, where they want you to put the angle first, so 4, then a 5, then press the sine button. In both cases, you should get the answer 0.707, and it goes on like 106781117, blah, 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 blah. But if you're not getting these numbers, please come talk to me, and I'll show you how to use your calculator properly. Otherwise, if you've got this value, great, you know how to use your calculator. Let's move on. Okay, so when light passes from air into water, so that tells me that the incident ray starts off in air, and the refracted ray will be coming out into water. So Ni is air, while Nr is water. It then goes on to say that it's entering the water at an angle of 60 degrees from the normal. So remember, we always measure from the normal. And this over here would be theta I, which is 60 degrees. And now it asks, what is the angle of refraction? So what is theta R? The angle from the normal to the refracted ray. Now the approach is to use Snell's law, Ni sine theta I is equal to Nr sine theta R. So now I'm going to start substituting these values in. Ni is the 1.0003. Sine theta I, which is 60 degrees, so sine 60 degrees. Nr is 1.33. And then I have sine theta R, which is what I'm trying to find. So over here, I'm going to press sine 60 degrees into my calculator, and that'll give me some ugly number. And when I multiply that ugly number by 1.0003, I get this ugly number over here. Now I'm going to bring out the other side, and then I'm going to divide out the 1.33, bring it over here, giving me 0.65134 after I divide these two. Now, I want just theta r, not sine theta r. To get rid of the sine, I have to use inverse sine. But because it's an equal sign, if I inverse sine on this side, I must inverse sine on this side as well. Now, in order to type in inverse sine 0.65134 ... on your calculator, you should be able to see the inverse sine button next to the actual sine button itself. So inverse sine is sine to the power of -1. We call that inverse sine. And you'll notice it's a slightly different color. That's because you need to press the shift key, which is the same color over here. So press the shift key, then press sine to access the inverse sine function. So one more time, to type in sine inverse, you must press shift, then press the sine button, and that will give you inverse sine. Now be aware, different brands of calculators, like for instance a Texas Instrument, they won't call it shift, they'll call it second instead. But it serves the same function. All right, so just click second, click on the sine button, and it's the same thing as saying shift and sine. So click on the shift, the sine, then type in your number and press the equal sign. And you'll get the answer 40.6428 ... But usually we round to just one decimal place, so 40.6 is good enough. Now again, some calculators want you to work backwards, so you got to type in the number first, then type in the shift sign, and that will give you the same answer in the end. Alright, so now that I've inverse sine the sine, we can cancel these two out, leaving me with just theta r. Meanwhile, the inverse sine of this number, we calculated it to be 40.6 degrees. So my angle of refraction under these conditions is 40.6 degrees. Alright, here's another one. A block of plastic is placed in water. A laser beam is passed from water through the plastic. So water into plastic, which means water is my Ni, while plastic is my Nr. Looking at my chart, I know the index of refraction for water is 1.33, and it looks like they want me to find the index of refraction for this plastic, so that's my required. Now it says the angle of incidence is 50 degrees, so the angle of incidence always measured from the normal, so theta I is equal to 50, while the angle of refraction is 27 degrees. So theta r, angle of refraction measured from the normal, is 27 degrees. Alright, so again, I'm going to use Snell's law. Ni sine theta I is equal to Nr sine theta r. Plugging these values in, I get 1.33 sine 50 is equal to Nr sine 27. I'm going to punch in sine 50 in my calculator, gives me this number. Punch in sine 27 in my calculator, and it gives me this number. Now don't round these numbers too early and not too much. Try to keep as many of the digits as you can actually. Otherwise, if you round too early, your final answer is going to be way off. Alright, so I'm going to divide out this number and bring it to this side. So now I have 1.33 times that weird number, sine 50, divided by sine 27, which is this number, and that equals to Nr. This results in an index of refraction of 2.24 for this plastic. Alright, now the last thing I want to talk about is called the critical angle. The critical angle is the theta I, the angle of incidence, that causes refraction to start turning into reflection. So it's the angle that makes the refracted ray come out horizontal to the phase boundary itself. Because anything more than theta I will start to get this one to become reflection instead of refraction. So this is the borderline where refraction turns into reflection. And whatever angle causes this to occur is called the critical angle. So let's pretend I'm going from water into air. What is the critical angle, the theta I, that will cause this to become reflection instead of refraction? Well, since I'm starting with water, I know that Ni must be 1.33. So I'll put that in. Now sine theta I is what I'm looking for. What is this angle that will cause it to reflect instead of refract? Now since air is the refraction medium, I know its Nr is for air, and that is 1.0003. Now finally, what is the theta r, the angle that will cause reflection to occur? Well, we always measure from the normal, and at this point, once you hit 90 degrees, anything more than 90 degrees now becomes reflection. So I can set it as sine 90 degrees, and that'll tell me anything more than that point, and I start to have reflection instead of refraction. All right, so now that I've got these values here, I can solve for theta I. So I take the 1.0003, multiply it by the sine 90, and of course divide by the 1.33, and then inverse sine this whole thing to get rid of this sign as well, and you're left with theta I equals 48.8 degrees. So the critical angle for water and air is 48.8 degrees. Anything larger than that angle, and we start to see reflection rather than refraction. So I won't be able to see out into the sky. I will only be able to see the bottom that is being reflected back to me. All right, and that is our lesson on refraction.